Hey guys, Harrison here. We're going to do problem number 10 this time for our video project number 3. So it involves a tank and us shooting a laser inside of that tank. And for part A, we're trying to find the distance from the laser to where it will end up in the tank, where the laser will end up in the tank. So in order to do that, we have to use this equation here, n1 sine theta 1 equals n2 sine theta 2, with the different indexes of refraction in order to produce an angle based off of the normal line of where the laser will refract to. So by doing that, we get 40.63 degrees, and then after that we use the SOHCAHTOA method of to find x1 and x2. So x1 is equal to 2.6 meters, and then x2 is equal to 1.72 meters, and you total both of those together to get 4.32 meters, and that is the total distance from the laser all the way to the bottom of the tank where the laser is refracted to.
Hey, it's Stephan here. I'm going to answer part B of this question. Part B is asking us, how would our answer to part A change, the total distance where the laser will hit at the bottom of the tank? How will that change if the medium N2 has a higher index of refraction than it did initially? And what's going to happen is, when this is higher, the angle at which this turns toward the normal will become more severe. So instead of hitting here, it'll end up hitting something like this, right down here. So what's going to happen is that the distance x2 is going to decrease, it's going to move this way, so the total distance is going to end up being smaller.
Okay. So for part C of the question, it's asking what do you have to change in the index reflection of N1, or the air, in order to make it so that none of the light is refracted into the water. So that's a principle called total internal reflection, so that the index, or the angle of refraction, is 90 degrees with respect to this normal, so that it all runs parallel to the surface boundary, and none of it refracts into the water. So that means that we want our theta 2 to be 90 degrees. Our theta 1 isn't going to change. It's still 60. It's the same as it's been the whole problem. Now we don't know what N1 is because that's what we're changing. N2 is the same. Again, it's the water. So we're going to take our Snell's law and we're going to change it around to get N1 by itself, which leaves us with N2 times sine theta 2 over sine theta 1. Now we can plug our numbers in, which is the index of refraction of the water times 90, or times sine of 90, which works out to be 1, over the sine of 60 degrees, and then that'll give us our index of refraction of 1.54, which is what it would have to be in order for none of the light to refract into the water.